So actually what I'm going to talk about is two very well-defined and simple to state graph estimation problem or matrix estimation problem, but here matrices will be 0, 1 symmetric for simplicity, so they are graphs. Okay? Many of these things can be generalized, but so the first one is the hidden subgraph problem or hidden click problem. So here I generate a random graph in this way. I take n vertices. I connect any pair of vertices independently with some probability q. Then I select k out of those n vertices, and I connect those with probability p. So this is the edge probabilities p if both vertices are in the special set S of size k and q otherwise. Okay, and actually often, it's hard enough to look at the special case p equal 1 and q 1/2. So the set S actually supports a click, a completely connected subgraph. Okay. So the problem is you are given a realization of this graph and you want to find the set S. Does the problem make sense? All right. How many of you can see the set S here? I can see it. Yeah, of course, the problem is that in reality, the edges are not colored. And they are not ordered, right? So how many of you can see the set S here? Volkan is, he has a non-polynomial machine inside this. Okay, the other problem is the following. I generate a random graph in this way. I take n vertices, and then I partition in two sets of sides n over 2, say n is even. If two vertices are on the same side of the partition, I connect them with probability p, and otherwise I connect with probability q. Okay, so the edge probability is p within the set and q across. And the problem is you are given such a realization of such graph, you want to find the partition. And of course, the problem also here is that they are not colored and they are not ordered. Okay? So do the problem make sense again? No. So the first time you hear about this, they look very similar problem, right? There is some graphs, and then there is some p and some q and some sets to find, and one might think it's just the same story, right? And here I will be looking at this problem from the point of view of detection thresholds. You can formalize it in many different ways, but I want to understand under which condition on p, q, n, k, etc. on the problem parameters you can actually find such a structure. You can actually detect the presence of such a structure and distinguish it from a purely Erdős-Rényi random graph with independent edges with same probability. Okay, and in this sense there are two thresholds to keep in mind, two conditions. And so I will refer to one as the classical statistics or information theory threshold. And this is the question, answers the question, is there any algorithm that can find such a structure? Is there any algorithm that can find the click or can find the partition? And then there is a computational question, is there a polynomial time algorithm that can find this partition with a probability or this? And if you have a polynomial time algorithm, of course, you have an algorithm, but vice versa is not true. And OK, so this is the executive summary, one slide. So now you can go away after this. And this is the picture, blurring over many details. For the hidden partition problem, there is a threshold. The problem becomes easier when p and q are well separated. And it's solvable where this ratio is above 1 over square root of n. And in fact, there is a polynomial type algorithm in that regime. So as soon as this becomes solvable with a probability, we have a polynomial time algorithm to find it. And for the hidden subgraph problem, and here, in that case, I will keep to p equal 1, q equal 1/2. So this is hidden click. The situation is dramatically different. Namely, it's very easy to see that to compute, show that the information theory threshold is 2 log n, basically. So we can, in principle, find extremely small clicks in a random graph. But despite 20, 30 years of research, nobody knows of a good algorithm, namely an algorithm that does it in polynomial time if k is smaller than square root of n. Right? So there is an exponential gap between the two. So these problems that look extremely simple, extremely similar, in reality they are widely different. And this really summarizes a lot of contribution, both on the hidden subgraph, starting, was introduced by Jerome, and then, there is a very important paper by Alon Krivelevich and Sudakov, and on the hidden partition problem. Okay, and if you want to summarize all of this literature, from a technical point of view, what comes out is that we have good tools to understand the information theory limits or statistical limits. We have good tool to understand when a problem is solvable in principle. But we don't have good tool to figure out whether a problem is solvable, a statistical problem is solvable in polynomial time. And the difference wouldn't be a problem if there wasn't gap between the two, but sometimes there is a big gap. The computational constraint is much more severe than an information theory constraint. So I think that the biggest question in this area really is the following: can we find good conceptual or good mathematical tool to understand computational limitation? Okay, so I want to talk about a kind of general approach, and then discuss what it gives in the hidden partition problem and the hidden click problem then. So the hidden partition has also been popular as community detection. So the general approach, so the difficulty in this business is proving lower bounds, namely proving that something is not feasible. It's relatively easy to prove computational upper bound. It's not easy, but we know how to do it. You find an algorithm, and you prove that it works, right? How do you prove lower bound? Well, this is complexity theory. Complexity theory is based on reductions, right? So in particular, well, you should reduce by from some complete problem. What is the issue here? The issue really is that we have to do with probabilistic models, statistical models. Our graph models are random. Reduction is not a good tool, or it's a very fragile tool in this context for two reasons. First reason, there is not a good complete problem. In complexity theory, there is satisfiability. You reduce satisfiability to traveling salesman problem, to whatever other problem you want to prove that is hard, and that's it. Here we don't have a good complete problem that is an average case hardness. I mean, there are some, but they are kind of. And then probabilistic models are fragile to reduction. If you construct a reduction, this typically changes the distribution in a dramatic way. There are exceptions to this story. There are cases of carefully crafted reduction among statistical problems. But these are very, you start with two problems that are quite similar to start with, and then you have to do a lot of work to construct your reduction. Okay, so this is an alternative or complementary approach that is analyze semi-definite programming hierarchies. So these are hierarchies of convex relaxation that are considered extremely powerful. So I put a new approach in quote because there are kind of old, or this was in theoretical computer science used since work by Uri Feige, Robbie Krautgamer in the early 2000s, but picked up in recent years due to the work of a lot of people in theoretical CS. Very beautiful work. And there is one semi-definite programming hierarchy that is the kind of golden standard, and this is the sum of square hierarchy. Okay, so what is the sum of square hierarchy? This really picked up after papers by Lasserre and Perillo in the early 2000s and was present in the Russian literature before. And think of it as a black box. You give it a problem, an instance of the problem, for instance, in our case, a graph, an integer d, and spits out a number that is the result of some convex optimization problem. Okay? And I will not describe this in general, I'll describe it in special cases, but important thing is that you can compute it in polynomial time for any bounded d. And this is considered, subsumes so many special algorithms, in particular so many special convex relaxation that, if you prove something about SOS, even theoretical CS people, believe that this is a real hardness result. Okay? Okay, so I'll start with a simpler example, that is the hidden partition problem. Okay, so I remind you, n over 2 vertices, and you connect probability P and Q. And okay, to make things nicer or more challenging, I really set P and Q to be a constant over n. So P is A over n and Q is B over n, where A is bigger than B. Why? Because it turns out that this is the most difficult regime. So we want to check whether this hierarchy, these SDP relaxations, work in the most difficult regime, or how well do they work in the most difficult regime. Okay? And I want to state, to set this as an hypothesis testing problem. Namely, I want to check whether the problem is, the graph is just an Erdős-Renyi random graph. So this is a random graph where each edge is present independently with the same probability, or it is distributed according to the planted partition. So you're given a graph, you have to say, it has a partition, it doesn't. And here the edge probability is set in such a way that total number of edges is essentially the same in the two models. So you cannot do stupid things just counting the number of edges. Okay? So this is my model. This means that I get graphs with bounded average degrees. The average degree of this graph is A plus B over 2. Okay, so the first question is, what is the information theory threshold? When is there an algorithm that solves this problem? Any algorithm. And this question was settled recently by Elhanan, Mossel, John Iman, and Alan Sly, and they proved that there is a test that succeeds with high probability that distinguishes these two the model with high probability, provided A minus B over square root of 2A plus B is bigger than 1. So this is how well separated are the edges probabilities, and this is somehow the standard deviation of the edge degree, of the vertex degree, right? So this is the difference in edge degree, vertex degree, and as long as this is bigger than 1, you're done. And this proves a conjecture actually by physicists. Right? So this settles this question. On computational thresholds, there is a long history that dates back to Dyer, Friese, Karp, and others. But eventually, the question was settled by the same people and independently by Laurent Massoulier, and they proved that this works. There is an algorithm that works as soon as the same ratio is bigger than 1. Okay, so under the same condition. Okay? So this is beautiful work, and if you look at these papers, what they do is that they carefully understand the distributional, the probabilistic properties of these graph models, and they craft an algorithm that exploits those properties in a very carefully way. So these are very smart people, understood random graphs, and then they figured out the right property to. So this begs the question, what if I'm not ingenious? This is not just an academic question. First of all, I'm not ingenious, and second, after all, we know that these models are all, false, right? So you want an algorithm that is robust with respect to the distribution of your graph, right? Something that is a bit generic. So if you are not ingenious, the first thing that you do is maximum likelihood, right? So what is maximum likelihood here? So I encode the partition as plus minus 1, so plus 1 in one side, minus 1 in the other. I call Aij the adjacency matrix in the of the graph. Maximum likelihood, if you think 5 minutes, is you want to maximize the number of edges on one side plus the number of edges on the other side. So this is sum over ij, Aij, xi equal xj, right? So, or equivalently minimizes the number of edges across the partition. Okay, subject to the partition being balanced and this being plus minus 1. Okay, so if you rewrite this in terms of xi dot xj, this is equivalent to maximize this quadratic form subject to this constraint and this plus minus 1 constraint. Okay, I want actually to get rid of this constraint, so what you can do is add it as a Lagrange multiplier. So I subtract a constant times sum of xi squared. If this constant is big enough, this kills all unbalanced partitions. And in fact, it turns out that the right constant to set is the average degree. I will not go into detail why that is true, but trust me, and we can talk about it. Well, so this is what gives here, it's the expectation of this A under the null model. If you choose these quantities, this is the expectation of Aij under the null model, because the probability that Aij is 1. So what you obtain, really, you can write this problem as maximize A minus expectation of A times XX transpose over all x's that are plus or minus 1 vectors. Now it's very nice and clean problem. Unfortunately, it's NPR'd. So what is SOS2 is just the first relaxation that will come to your mind. That is, I replace XX transpose by a semi-definite, positive semi-definite matrix with xii equal 1. This is sometimes also called the Grothendieck problem, or the Grothendieck relaxation. Right, and what is the test now? Now we forgot about the test. What you would do if you could solve maximum likelihood, you would say, okay, if there is a big value to this problem, a very good cut, I'll declare that there is a partition, otherwise I declare that there is no partition, so I'll do the same with the SOS value. If the SOS value is bigger than a constant, then I'll say 1, otherwise I'll say 0. Does that make sense? Okay, so we rushed through these slides. Some of you, this is obvious. Some others of you, this is not completely obvious, but trust me, this is really off the shelf. You teach master students that take the first class in convex optimization how to do nowadays, how to do such a relaxation, right? So it's really a not ingenious algorithm, I claim. Okay, so how well does it work? So this is a theorem that we have. This test works provided, for large. So this works. This is a theorem that it's true for large A plus B. So the degree is bounded by large. So it's not any bounded degree, but the degree bounded by large. So this magic ratio has to be bigger than 2 plus some small law of A plus B. Okay, so a couple of comments. So what this tells you really, remember the information theory threshold says that here there should be a 1, and it says that SOS2 is at most suboptimal by factor 2, roughly. And in fact, the 2, I think it's an artifact of the proof, I'm quite sure. And modulo a random matrix theory conjecture, a difficult one, should go to 1. So this same SDP, of course, was analyzed by others before, and the best result before this was by Guédon and Vershini that proved basically the same with a slightly worse constant. Okay, and okay, in a different regime also, but Abbe and Bruce Hayek and collaborators. All right. You can do this in practice. You can simulate this SOS and see how it works, and actually it works extremely well. So this is for average degree 10. This is the information theoretic threshold, and here what I plot is a measure of accuracy of the reconstruction for different size. And what you see is that as below the information theory threshold, as the size get larger, this accuracy goes to 0. So here, in large n limit, you expect that it not work, while a little bit above, it seems to go to a positive constant. Okay, so simulations seem to show quite clearly that the threshold is really either 1 or very close to 1. Okay, hopefully we'll be able to prove it. Now, there is actually the best part of this result, in my opinion, is a lemma. Okay? And there's a lemma that gives a sharp characterization of this SOS under the null model, that is the pure Erdős-Renyi random graph. This, I like it because it has an equal instead of a bigger or equal. And the equal is the following, that if you run SOS in a purely Erdős-Renyi graph, you obtain 2 square root of gamma. Gamma is the average degree, plus a small o square root of gamma. Okay? So I don't expect many of you to react to this theorem. But if you know random matrix theorem, this should strike you. If you look, this is very different from what happens to the spectral relaxation for this graph. Spectral relaxations work very badly, but SOS works very nicely because it kind of spreads the eigenvector. you add this additional constraint on the diagonal that forces the eigenvector to be bounded. Okay. Okay, I'll add one thing. If you further relax this problem, you can further relax this problem, right? And look it over vectors of norm 1, or equivalently maximizes over matrices of trace equal to n. You get a spectral problem whose value is the maximum eigenvalue of the matrix. Now, the maximum eigenvalue of such a random matrix is not of this order, but is of order square root of log n over log n. So it's much bigger. And the maximum the corresponding eigenvector is completely picked on one vertex. Okay? So by putting these diagonal entries equal to one constraint, I was able to somehow force the eigenvector to be completely delocalized. Okay. Next 10 minutes, I want to talk about hidden click. And now we will doing, so the punchline was for this hidden partition, just the first level of the hierarchy. Basically, odd levels, even levels are better. So you do 2, 4, 6, etc. So the first level is basically solving the problem. Now we look at the hidden click and we look at the second level. Okay, so again, this is a problem where you have a matrix and then I plant a click of size k in it. So edge probability is 1/2 here and 1 here, despite the figure. Right? So I want to distinguish between two hypotheses. Under the null hypothesis, each edge is present with probability 1/2. Under the alternative, edges in the set S are present with probability 1 and outside with probability 1/2. Right? So we change the problem. And again, information theoretically, this you can solve when k is bigger than 2 log n. And this is basically a graph theory lemma that is due to Grimmet 30 years ago or 40 years ago. And there is all sorts of generalization. Now, the story for computational threshold is much shorter. Right? So the simplest thing you can do is just count edges in this graph. This works as soon as k is bigger than square root of n log n. Now, in a very important paper, Alon, Krivelevich, and Sudakov came up with an algorithm that works as soon as k is bigger than any constant times square root of n. Okay? This is a spectral algorithm. And okay, there have been many people working on this and many papers, but basically there has been no progress on this question. Okay? So these kinds of points to suggest that the square root of n is a fundamental barrier, or we don't have good ideas of how to overcome it. Okay, so how do you formulate it? We want to formulate it as an optimization problem, as we did before, right? So this is one way to formulate it as a 0-1 integer program, right? So a vector that is in 0-1, oh, here there is a sum, this j shouldn't be here. So a sum over I of xi, so I maximize the number of 1, subject to what? Well, every time I have ij is not an edge, I say that xi times xj must be 0. At most, one of the two of xi of I and j is not in the click. Because if I is in the click, it's vertex I in the click, and ij is not an edge, then j is not in the click. So xi dot xj must be 0. Okay? So this gives one constraint per each non-edge of the graph or edge of the graph complement. So this is my optimization problem. And SOS is really a semi-definite program with not n variables, but a polynomially larger number of variables, n to the d, or n to the order of d variables. And the intuition is that this captures all correlation between up to d variables in your graph. Right? If you think the most naive relaxation is you relax the constraint 0-1 to the interval 0-1, you can interpret this as relaxing an integer value to a probability. So here you don't take only account probability of each vertex, but correlation among subsets of d vertices. Okay, so now I'll define the SOS relaxation for this problem for general D. It takes a little bit of notation and I think 2 or 3 slides, but perhaps for those of you who never heard about this is the most interesting part of the talk. Not the theorems, but It's very natural construction. Right? So I denote by this the set of first-time integers. And in this way, the subset of this set of sides equal to L. So this is, for L equal to, this is all the pairs, for instance. And this is the subset of sides n of sides at most L. So for L equal to, this is the empty set, all the singletons, and all the pairs. Okay? And the SOS has decisions variables that are functions from this set of duples to the interval 0, 1. So for each S, for each set S, I get a number x of S. Okay? So this is a function, but really, since it's a function of finite space, it's really a big vector that I can do computation with. Okay, so these are my decision variables, and it's convenient to keep in mind the interpretation. And interpretation can be made actually very precise, but let's keep it at an informal level, because I don't need it. And interpretation is the following. This x of S is the probability that the whole set S is in the clique. Think of the simplest relaxation. You relax xi to xi in the interval 0, 1, then you interpret xi as the probability that I is in the clique. Now you relax xs as the probability that the whole set S is in the clique. Out of this set S, I construct a moment matrix that indicates as a moment of X. This is indexed by subsets of sides at most d over 2. And the definition that moment X entry S1, S2 is defined as X evaluated on S1 union S2. So if you think of the interpretation matrix, you understand the meaning of this name, moment. Why? Because this is the probability that S1 is in the clique and, typo, S2 is in the clique. Right? S of X1 and S2 is the probability that these two are both in the clique. This should be an S2. Right? So it's a moment. Okay, and what is the relaxation now? The relaxation of this problem is the natural thing that you will write, right? You want to maximize this in 0, 1, so I maximize the sum of the probabilities that I is in the clique. So the expected size of the clique, if you think this still has a probability. Subject to, well, X of the empty set has to be 1, because the probability that nothing is in the clique is 1. The empty set is always in the clique. Moment matrix must be PSD, because this is a moment matrix. And every time, so all of these are problem generic constraints. These have nothing to do with the fact that we are talking about the clique. This is the problem specific constraint. Every time, look at a set S and call GS the subgraph induced in G by S. So for instance, if S is a triple, GS is the subgraph induced by those 3 vertices containing all the. If this is a clique, is not a clique, then X of S must be 0, because S cannot be a clique, cannot be in the clique. Right? So again, if S, for instance, it's a pair, this is saying that every time the pair vertex is not connected by an edge, then Xi, j must be 0. If S is a triple, this tells you every time that I, j, k are not connected by 3 edges, then X of I, j, k must be 0. So again, we rushed through this, but this is again really off the shelf, right? I mean, people developed apps for us. Building this relaxation is just an exercise. It's, once you understand how these things work, you write it in half a page of your notebook. And the more you think about this problem, the more you realize that basically any idea that you have is subsumed by some of this relaxation. You start, when you first see this problem, you start coming up with heuristics. I'll count number of vertices that have degree 5, subtract number of vertices that have degree 6, and count the cliques of sides 7, etc. They are all special cases of this. And the question is really, how well does it work, right? Okay, it works poorly. It doesn't work at all. Which is good, right? Because we want to prove that this problem is hard. After all, lots of smart people worked on it, and they didn't find ideas. So we want to tell these smart people, hey, don't get depressed. Okay? So this is a theorem that we had early this year. appeared in Colt, and that was a few weeks ago, says that SOSG4, so we looked only at the next level. But if you think of it, this is already a very complex algorithm. It's time complexity at least n to the 4 or n to the 6. Unless then k has to be bigger than the power of n, and the power is n to the 1/3. And this twiddle hides polynomial log polylogarithmic factor. At the same time, more or less, there was an independent paper by Ragumeka, Aaron Potechin, and Avi Wilgerson that proved that SOSGD fails unless k is bigger than n1/d. So this result is stronger in sense that looks at any d, but is weaker for d equal 4. So this is a more careful analysis that very carefully analyzes the construction for d equal 4. Now these are lower bounds, and we saw that smart people weren't able to find anything for k smaller than square root of n. So one would expect that these lower bounds are improvable to square root of n. So there is a gap between n to the 1/3 to square root of n. One would expect that this would be improvable. Okay? So I'm used to the fact that you work on a problem that is exciting, and there is other people, and there is multiple papers that come up at the same time. Interesting for this problem, there were 4 papers coming out in a span of a couple of months. And this is actually couple of weeks, last week or 2 weeks ago. So there were 2 papers by, one is Raghavendra Shram, one is Hopkins, Kotari, Potechin, so this is Berkeley and this is MIT. And so basically they fill this gap for SOS4. So SOS4, now they proved that it fails unless k is bigger than square root of n. And at least this proof, I didn't see the details, but this proof uses a lot of our technical analysis. We got exhausted with it, but they pushed it forward. I mean, there is an idea, an additional idea here that it's important. Okay, of course, this doesn't finish the story even on the analysis of SOS for the hidden click. The conjecture is that SOSGD needs k bigger than n to the 1/d divided by a constant to the d. And actually in 2013, Meka and Vigderson had a paper that claimed that this result with a log factor suboptimality, but the proof was based on some matrix concentration inequality, and it had a bug. But this is a beautiful paper, and actually is the paper that got me interested in, despite the bug, that got me interested in the whole story. And as you can see, this is much less understood than the hidden partition problem. Okay, so I tried to convince you that SOS, it's an interesting tool for statistical problem. We proved we looked at it in the hidden partition, and there we got an achievability result, and we get fairly precise result. We still have a factor 2, but hopefully can be improved. In the hidden click, we used to prove a lower bound, and still the picture is very coarse there. It seems a much more challenging problem. Thanks.
Thank you, Andrea. Questions? Many questions?
Yeah, I just have a question on the issue when you don't know the number of cliques. In that case, there's another problem in back of this, right, which is estimating D. So estimating the number of partitions. So
okay.
Do these results address that in any way?
So we looked at applied the hidden partition with this set. We didn't write it up, but we got basically that you can construct the generalization of this SDP and get the test. So we tested 0 against D, but I would think that it's not inconceivable that the same proof extend to testing D against D1 against D2
yeah.
for any bounded number of values.
But there's probably a penalty, an additional penalty, right, of log of D or some.
Well, I'm saying any. I don't think so, but yeah. I didn't. We tested 0 partition against D, and we got the same factor 2 that I think it's an artifact of the proof. But,
I see.
yeah, it's a good question. We should look at it.
So in the theorem on the hidden partition, which was a success theorem, like the algorithm, the SOS succeeds, I suppose the solution of the semi-definite program, capital X, is a rank 1? Because
no, interestingly, it's not.
it is not. So
yeah,
how?
Because
so how do you get?
This is very important because you know, otherwise you would be solving the maximum likelihood problem. This doesn't solve the maximum likelihood problem.
So how do you obtain the little x?
If you want to do estimation, well, that's you know, okay. In this plot that I showed, what we do is something very simple. We take the matrix, the solution of the SDP, and then you do PCA. You take the principal component, and then you take the sign of this.
I see.
That works fine.
Thank you.
There was one by.
So I'm sort of wondering, you were discussing, if I understand correctly, the case where the matrix is known. But what if the matrix is being observed, you know, estimated through noise? And to take it to an extreme, imagine that part of the matrix is available and other parts of the matrix are unknown. Can you make any comments on that type of problem?
Well, you know, there is this work, for instance, on. Yeah, I think that as soon as you have this sparsity plus low rank, I mean, there is lots of evidence there that these problems are generically hard, and I think the same will happen. I mean, this theorem of SOS, actually, we don't do it only in the graph setting, but also we do the Gaussian version, right? Because where you have a rank, sparse low rank, plus Gaussian noise, basically. And you know, basically you get similar gap in that case. We prove a similar gap. Now, missing entries, I believe, should give a similar picture. But yeah, it's an interesting question. There was one question.
All right, I think this will be the last question.
I enjoyed the talk. One question, there's other semi-definite programs to find large cliques. For example, the Lovash theta function is a semi-definite program that finds the maximum cliques on some graphs, you know, so if the graphs are perfect or some other properties. How is it related to some of the semi-definite
I think
programs?
Lovash theta function is basically comparable to SOS2.
I see. But there are some
Lovash
different...
theta function is normally stated for an independent set, but it's basically is an SDP of sides n by n, or order n by n. So it's comparable to SOS2. So there is another hierarchy that builds, basically, I think it's related, that is the Lovash-Scriver hierarchy, and it's strictly weaker than the SOS hierarchy, for instance. So,
Okay.
So this is really, you know, for combinatorial problems, I think there is no natural example of anything, any relaxation that doesn't fit this hierarchy.